talk about the shortest path problem, and we have different versions of it. We start with a directed graph that's weighted. Each edge has a cost associated with it, and the goal is to find the shortest path, that is to say, the path of least cost. And in the single pair version of the problem, we're trying to find the shortest path from a given vertex S for start to a given vertex T for finish, I guess. And in this case, with all these weights, the cost is 5 in the shortest path SBDAT. Now the single source version of the shortest path problem is that you pick a source vertex, which we'll typically call S. And then the problem is to find the shortest path from S to every other vertex, which of course creates a tree structure that looks like this. But the way that this is stored as in the computer is by using back pointers. And for each vertex, the back pointer points to the previous node in the shortest path. So for example, T with this point here and this point's here. And we think of the back pointer as always pointing to the previous node on the shortest path from S to X, to S to that node. A solution to the single source problem looks like this. There are two arrays, one of which shows the minimum cost from S to each node, and the other gives a back pointer for that particular node. And the way it can be solved is in several different algorithms we have, the simplest which is dynamic programming. And in dynamic programming, you first have to visit the nodes in topological order. And this is required that G be acyclic. All right, so in this particular example, a topological order of the nodes would be S, B, B, D, A, C, T. And so we visit them in that order, and in each visitation we update the values of the costs and the back pointers. So initially, of course, the source has cost 0 and the back pointer is undefined. Now, when we visit, the next one we visit is D. No, B. And there the cost is 2 and the back pointer is S. The next one we visit is D, and there the cost is 3 and the back pointer is B. Now why is it 3? You take the cost of B and you add 1 to it. All right, now in the topological order we have A. Now in A's case, we have a 0 here, and we have 2 here, and we have 3 here. Now in A, you either can come from a 2 and add 5, or come from 3 and add -1. Now it's clear that this direction is better. So for A, your cost would be 3 plus -1, which is 2, and the back pointer would be D. All right, the next node in the topological order is C, and we can only reach it from a D, and the D has a cost of 3, so that makes this a 7. So this becomes a 7, and the back pointer is D. Now when we get to T, we have two things to look at. 3 plus 7 is a possibility, and 2 plus 3 is a possibility. Well, guess what? We're going to pick 2 plus 3, and that comes from A, so the back pointer is A. And this is the complete solution to the min-cost problem for the case of this particular graph, for the single source problem. One of the things we're interested in is bunch of algorithms for the single source problem. Now, the single pair problem is not as important as the single source problem. In other words, we have more algorithms for single source. Now, we're going to use this notation. N is the number of vertices in the graph, M is the number of arcs, and L is the maximum number of arcs in a shortest path. Now, if we look at this graph here, let's call this G, there are 4 vertices in this path. There are 5 arcs. But the shortest path from S to anything else never has more than 2 arcs in it. Now, it's true that there is a path that has 3 arcs. However, it's not the shortest path from S to C. Therefore, L is 2. Now, we're looking at different algorithms for the single source problem. Recall N vertices, M arcs, and L for the shortest, fewest number of edges in any shortest path. Now, we're going to look at 3 algorithms here. The dynamic programming algorithm I just showed you. And one restriction is that the graph has to be acyclic. The time complexity is very short, n plus m. The Bellman-Ford algorithm does not require it being acyclic, but it does require that no cyclic has a negative weight. In other words, if you go from x to y and eventually back to x again, that's a cycle. And the total weight of all the edges on the cycle is not allowed to be negative, or else the algorithm will never converge. And the time complexity for our implementation of Bellman-Ford is m times L, where m is the number of edges and L is the length of the longest length of any shortest path. Now, you can see in books that this would be written as m times n, but L is always less than n, and in some cases it's a lot less, and therefore that's a big difference. I'll give you an example. If you take the internet and think of the graph consisting of all internet pages, and the arcs are links. There's an arc from page X to page Y, meaning that there's a link on page X which gets you to page Y. Now, the number of nodes in that, number of arcs would be very large, and the number of nodes would be very large. So if you have nm, that's very, very large times very, very large, which could overwhelm your computer. However, L is not very large, and therefore ML is possibly even doable. Now, the most famous algorithm here is Dijkstra's algorithm, which everybody's heard of, and one rule is that none of the weights is allowed to be negative, which is not the case here. Here we can have negative weights, here we can have negative weights. And now our requirement, our time complexity is pretty short. It's m times log n instead of m times n, which is what you might think. Now I'm going to explain one of these algorithms, the Bellman-Ford algorithm for the single source min-path problem. We start with the weighted directed graph V, E, where E is the set of arcs. I'm going to list them this way. So there are m of those. And remember, there are n vertices, but we don't have to list them to describe the code. Here is an example of part of the graph. We have to assume that this is a part of G. All right, now, the idea is that as we iterate through the main loop L times, where L is the maximum length of any shortest path, we might not know what L is, but for the moment, let's assume that we know what L is, because typically L is actually quite a bit shorter than n, although the maximum value of L is n minus 1. That's typically not the case. All right, now, we initialize the cost, which is then cost of shortest path. For the source, the shortest path from S to S has length 0, of course, and since we haven't built any paths, the cost from S to any other vertex is infinity, meaning that we don't have a path. So we have nested loops. This is our main loop, and in some sense it's a dummy variable t. It just keeps track of how many times that we've iterated it. And we're going to iterate it L times. And the reason is this: after a certain number, after t iterations of the main loop, we will have the best path from S to every vertex which has no more than t edges. All right, so we'll proceed here, and we look at the edges one at a time. Remember, we've numbered the edges, and let's say we have the edge EI. Now that edge is going to be equal to an ordered pair of vertices xi and yi, and that edge will have a weight, which is w of I, we'll call that. W of I, the weight of that edge EI. All right, now, in the picture over here, I have xi, yi, and here I'm assuming that that t is actually 3 at this point. So we have computed all the shortest paths of no more than 3 edges. So right here, the cost of xi is 9, because that's what we have so far. The weight of the edge EI is 5. Now the cost for yi is the cost of the shortest path of length no more than 3 edges, which will be 6 plus 7 plus 8, we're assuming, which is 21. There. Now when we compare that, we are looking at a new possible path, which is to combine the shortest path to xi with one more edge. And that would be 9 plus 5, which is 14. So what do we have here? We're going to ask whether 9 plus 5 is less than 21. Is it? Yes, it's less than 21, which means that we will replace cost yi was 21 before, but now it will be 14, because it's the sum of 9 and 5. But then the back pointer. Now before, the back pointer for yi pointed to this vertex. I didn't name it, but let's say this vertex is z. And this points to z. But here we have to define a new back pointer. The new back pointer of yi is xi, because the new shortest path is here, which goes through xi, and so that's the correct back pointer. Now the next thing you might wonder is, what happens if we don't know the value of L in advance? And I actually have shown you how to do that in class. What you do is, during each iteration of the outer loop, you check to see if any value of cost has been changed. And if it has, then you might not be finished. But if at a certain iteration of the outer loop no changes have occurred in the cost array, then you know that there will never be any more, no matter how many times you iterate the outer loop, which means you can now stop the outer loop.